Hey there guys, welcome to Unit 5 Note C. We're going to focus on hydrates for this lesson. So what is a hydrate? In order to have a hydrated compound, think of the word hydration, you would need a certain number of water molecules to be attached to that compound. So a hydrate would have a set number, and that's kind of going to be the point of the lab, how many, a set number of molecules that's going to be attached to that central compound. So some definitions before we get too far into it. The hydrate itself would be the molecule with the attached water. But part of what we're going to be doing is removing that water. So if you do that, if you're able to drive off the water, you would form something called the anhydrate, which is basically the part of the molecule that would come before the dot that shows the attached waters. So that would be just like your ionic compound usually. In order to remove the water, you would have to go through a process called dehydration. And even though these hydrates are typically solid, we still call this dehydration. We're still driving the water molecules off. Removing water is called dehydration, any form. All right, so let's break down a hydrate. Here's an example. You may remember things like this when we looked at the molar mass examples. This attachment is simply a connector. It is not a multiplier. So it shows that the magnesium sulfate is connected to 7 water molecules. Okay? The part that's before the dot would be our anhydrate, would be the part that does not have water in it. And when we go through dehydration, the idea is that's all we're left with. The part back here is not called the hydrate. It's just called water. It's one of my biggest pet peeves. The hydrate would actually be this entire compound. That's simply the water attached to the anhydrate to form the hydrate. If we wanted to form the anhydrate, we would dehydrate or remove the water. Just kind of seeing how this all comes together here. This number on the water molecule is known as the hydration number. And it's what's going to be our point of the lab, or our purpose of the lab is going to be to determine the hydration number for a hydrate. So it shows how many water molecules are attached. Certain formulas come with set numbers of water molecules. All right, so there's your parts of a hydrate. Connector, water molecules with a count on them, and then our anhydrate over here, with the entire thing being called the hydrate. All right, let's look at an example. Keep in mind that the dot in the center is just a connector. I have some questions about this molecule. To start off with, how many carbons, oxygens, and hydrogens are there? So you've got to be really careful, for one, about your parentheses, and for two, about how this shows a connection to water molecules. So let's count the carbons first. I have 1 inside the parentheses, but I have a 2, meaning I have 2 of everything in the parentheses. So I'm already up to 2 carbons. In the water part, there are no carbons. So actually, there are only 2 carbons. The oxygen, though, is everywhere. So let's look at the oxygen next. Inside the parentheses, I see 2 oxygens, but there's also the 2 outside the parentheses. So that would double what's in the parentheses. So 2 doubles to 4 now. This shows 2 water molecules. So if I have 1 oxygen in each water, but I have 2 waters, now 4 goes up to 6. Now let's look at the hydrogens. So I do have a hydrogen in front of the dot, 1 in the parentheses, but again, there are 2 of everything in the parentheses, so we're already at 2. But then there's also 2 per water molecule, and with 2 water molecules, that's now 4. Added to the original 2, I also have 6 hydrogen atoms. So I have 2 carbons, 6 oxygens, and 6 hydrogens. What would be the formula for the hydrate? So this is kind of quizzing on parts of the hydrate. So what would you say is the entire hydrate formula? That would be this entire substance, going all the way from the beginning parentheses to the end oxygen would be the formula of the hydrate. So what would be the anhydrate? That means I just want to stop at the dot. So the anhydrate is the part in front of the dot, just the COOH with a 2. It's everything in front of the parentheses. And then last question, how could I form the anhydrate from the hydrate? How could I get rid of the water? Remember, that was a process called dehydration. All right. Now let's do something a little different with this molecule. We've looked at percent composition before, or mass percent for chemistry. I want to do it for the hydrate, but not exactly the same way. Instead of breaking it down per atom, like I did with the regular molecules, with the hydrate, it can be much more useful to break down the percent anhydrate compared to the percent water. So that's what I've got here. The molar mass of just the COOH2. Save us a little bit of time. Remember, you would just add up the molar mass of each atom. That's going to get you 90.04. But then the molar mass of the entire compound is 126.08. So could I get the percentage of anhydrate? So if I'm interested in percentage of anhydrate, I would put the anhydrate part that I'm interested in on top, 90.04. I would put the entire mass, the 126.08, and then multiply that by 100. And that's going to get me the percentage of anhydrate. If I was interested in the percentage of water, I could do that one of two ways. I could either find the molar mass of water twice and put that on top, divided by your total 126, or you could take your 126 and subtract your 90. The difference in mass lost must be the mass of the water. And that's a huge important detail. Conservation of mass. Whatever mass is lost would have to be the mass that was driven off during the dehydration. So that's going to allow us to kind of deduce our mass of the water, even if we didn't know exactly how many, like if we didn't have that hydration number. All right. So for the percent anhydrate, you should get 71.4%, and then getting the two water molecules masses to be 36.04. Either of the two methods I talked about will get you that number, and then it'll be 28.6. Notice, just like with regular percent composition though, these two numbers should still add up to 100. So that's how we can get our percentages for the different parts. Now, why is that useful? Where can that come in handy? So let's look at another example. Here I have calcium nitrate attached to 4 water molecules. And it says I'm going to heat it to something called constant mass. So what do you think heating a hydrate would do? Well, it's going to facilitate the dehydration, right? So if I heat it, different color, hold on. If I heat it, that's going to mean I'm removing the water. What would be left when I have completely heated off the water or completely dehydrated the compound? Only the anhydrate. Once I have removed all the water, there's nothing else to leave. This bond is not going to break. Remember the ionic bond being the strongest bond? So say I have my calcium nitrate, that's not going anywhere. And I have just 4 water molecules around it. As I heat it, maybe one will leave, mass will drop a little. Another one will leave, mass continues to drop. More water leaving, continuing to drop. Once I've gotten rid of all of the water, nothing else is leaving. So would the mass change? What would you call a mass that doesn't change? Constant mass. So this is a big deal in the lab too, reaching constant mass, literally a mass that doesn't change. Once we have constant mass, that's your evidence that you have formed the anhydrate. All right, so let's look at the math on this now that we've kind of talked procedure. All right, so it says there was a 7-gram total sample. If I could figure out how much anhydrate, how much of the mass the anhydrate took up, I could then figure out how much of that mass would be left after the dehydration. I need to know how much anhydrate versus how much water, and I can find the percentage of the 7 grams. So let's start with finding the molar mass of our calcium nitrate so we can find our percentage anhydrate. So you're going to look up your molar masses on the periodic table for calcium, nitrogen, 3 oxygens, double your nitrogen's mass. What is that total molar mass? There we go. 164.1. Then if you also included the molar mass of the 4 waters, you would get 236.18. So this would be the entire hydrate then. 236.18 grams. So that's going to give you the percentage of anhydrate for the entire compound. So we get about 70% of the compound that's anhydrate. So if I drive off all of the water, I would be losing about 70% of the substance. Well, if I know I have 7 grams of the substance, that means I would be losing about 30% of the 7 grams, or I would be keeping about 70% of the 7 grams. So how do you find the percentage of a number? Well, if I'm interested in finding the percentage of 7 grams, I want to take that mass and multiply it by the decimal version of the percent, which is going to be 0.695, keeping the 1 decimal place for percentages. I'm going to multiply that by the 7, which is going to reduce the sig figs down to 2. And I'm going to be able to find the mass of the anhydrate that would actually be left of the real 7 grams, which is 4.9 grams. That kind of represents about 30% of the substance being dehydrated as we reach constant mass. So you want to find your percent anhydrate and then find that percent of the total mass. All right. So let's talk naming a little bit. When you name the hydrate, you are going to name the beginning part using your same old formula unit rules. So magnesium is just magnesium. Sulfate has the right number of oxygens, so it's just sulfate. What we really need to focus on naming is the number of water molecules. Fortunately, the way we're going to number those, the way we're going to name those numbers is using the molecular prefixes, the same ones that we learned when we were learning how to name molecular compounds. So hepta means 7, and then you're going to end with the word hydrate. And so I know this is kind of where people get confused thinking hydrate means water if you're just reading left to right, but the hydrate's actually referring to the entire compound being a hydrate, which you should know means it's attached to water. So you're going to call it a heptahydrate. If the hydration number was 4, you would call it a tetrahydrate. You're putting the molecular prefix that matches the hydration number on the word hydrate. All right. So first you name the formula unit normally. Then you're going to use the molecular prefix and then the word hydrate. So let's try LiClO4, careful with that 4, attached to 3 water molecules. What would we name this? Well, this is lithium, not chlorate, but 1 extra oxygen. So in this case, you use the per prefix. So this would be lithium perchlorate. And then what does the 3 prefix use? Tri. So it's trihydrate. Lithium perchlorate, trihydrate. All right. There is something else you have to do when you name the anhydrate. After you've dehydrated a substance, the molecular structure is actually compromised. Like the crystal structure of the way it's formed is different. Think about when you turn a grape into a raisin. You dehydrate it, or you pull the water out of it. You can't then turn around and try to sell those raisins as grapes. They're raisins. They have a different name. So you're not going to totally change the name in a situation with the anhydrates, but you should kind of warn people, hey, you're getting something that's been dehydrated. So you're going to see anhydride or anhydrous, used as an adjective, tagged onto the actual name of the substance. Just to kind of let people know, hey, this was a hydrate and then we dehydrate it, so it is a little bit different. So you have this anhydrous barium chloride. All right, so if you need a break, here would be a good time to pause, because the very last thing that we're going to do is go over the exact same calculation that you're going to do in the lab. We're going to walk through it with some sample data. All right. So with this example, we're using a hydrate called strontium nitrate, and it's attached to some number of water molecules. What it gives me is the mass that I completely start with in the very beginning when it's still hydrated, this 15.35 grams, but then also it's giving me the constant mass of 11.45 grams. So this would represent the total amount of the sample that I'm starting with, and this would represent the amount that's left after dehydration is complete. So let's think how we would actually do this in the lab. First of all, we would need something to hold the substance in. You can't just throw chemicals on a scale. they have to be in something, right? So we're going to put them in something that's actually designed for evaporation called an evaporating dish. Fancy name, right? You put your substance in here, and in this example, that initial mass is 15.35 grams. Then I need to go through this dehydration process. I need to achieve constant mass. So this means I need to put it on a flame. So we're going to put it on like a Bunsen burner flame, and we're going to apply heat. The heat will then cause the water molecules to start to leave. The question is, how can I tell I've reached a constant mass? Kind of indicates we would need multiple mass readings, right? So the idea is you would take this substance off the flame onto a scale, and then back on a flame, take it off to the scale, back to the flame, back to the scale, back to the flame, back to the scale. And you should be seeing this number drop. So let me do this over here. Say we got 15.35 grams to start with. You'll probably drop down to like maybe 15.2 grams, or then keep going down to 15.13 grams and keep going down. And it might drop, it probably would drop actually a little faster than this. Let's go ahead down to 13 grams. And then let's say I go ahead and get to this 11.44 grams. Let's speed this up a little bit. In order to get to constant mass, I would need to get that same number, ideally 3 times. Like literally 2 decimal places out, same exact number, 3 times. Once I have achieved that exact same mass reading, then I have achieved constant mass. And what that means is now the only thing left in the dish is the anhydrate. I've gotten rid of all the water. So all that's left here now, in this example, would be the strontium nitrate. We'll have a different hydrate for our lab. But with this example, that's the anhydrate, and so that's what's represented by the 11.45 grams. So then the first thing that we're going to have to figure out is how much water left. If I know I started with 15.35 grams and ended up with 11.45 grams, I could find the difference in those two numbers, and that would have to be the mass of the water that left. Due to conservation of energy, I know that mass didn't just disappear. And what's the only thing that has left the substance? The water. So the mass difference would be the water difference. Here's the one last catch before we get into the math on this. These numbers represent the actual substance's mass, but the fact that it has to be in this evaporating dish is going to cause a complication in having to read the scale. Right? It's going to have mass too. And so if we've got the dish on the scale, that would contribute to the mass that we're reading. So one trick could be to zero the scale and then add the 15 grams. But then you're going to have a problem when you get down here to the 11.45 grams. How am I going to find the mass of just that substance when it's like baked into that evaporating dish? Well, the solution is something I want you to come up with for our lab on Thursday. How is it that we're going to be able to find the mass readings and be able to calculate the masses of the individual substances without that dish being a problem? So we got to think practically on that. All right. That's as much hint as I'm going to give you for lab. Let's get into the math. All right. So we talked about subtracting the masses. This was my original mass, and this is our constant mass. And what left must be the mass of the water. So that would be our 3.99 grams. Law of conservation of mass states that can't disappear. So there we go. Once I do this, I actually don't even need my initial mass anymore. What I want to do is compare the amount of anhydrate to the amount of water. So I'm going to compare those two things. I can't compare gram to gram. There is only one unit, universal enough, to compare two completely different substances. What's the most universal unit you can think of? Well, of course, moles. Awesome, moles. Mass loss has to be water, got that? So here we go. We want to get our moles of the anhydride. So with the anhydride, that was the constant mass, the 11.45 grams. So this 211.64 would be our grams of the anhydrate per mole. What do we call that number again? Those are molar mass. So we're doing our conversion factors just like we did in the beginning of this unit. So we're using the molar mass to be able to convert to moles. So we got 0.05410 moles of this strontium nitrate. Now I want to look at the amount of water in moles. So how much water did we start with? That was that mass that was subtracted, right? Our 3.90 grams. And then I'm using the molar mass of water to convert to moles of water. So you first do your subtraction to get to grams, and then you have to convert gram to moles. Now we're almost there. Once I have moles, now I can compare. So how do you compare two numbers? You use a ratio. So if you put the amount of water over the amount of strontium nitrate or anhydrate, you're going to get water per anhydrate, which is exactly what we want. This will give you a hydration number of 4. If you actually divide the number of moles of water by the number of moles of the strontium nitrate, I should say moles in here, take our moles and actually form a ratio out of them, then I can see I have a 4-to-1 ratio. So if I have strontium nitrate and I'm trying to figure out how much water it's attached to, this would represent 1 strontium nitrate and then how much water? It was a 4-to-1 ratio here. So that means my hydration number is 4. So once we know the hydration number, we can actually name it as well. So if it's a hydration number of 4, you're going to have a tetrahydrate. So this is our goal. Identify the hydration number, plug it in the formula and the name as well. So just to recap the steps one last time. First, you've got to subtract your initial mass from your constant mass to get your water. Then you take your anhydrate and your water, you convert them from grams to moles, and then you do that ratio of water per anhydrate. That's going to give you our hydration number, and then you've successfully completed the lab. All right, so that's going to wrap up our notes on hydrates. The next notes that you're looking for will be Unit 5 Notes D on molecular and empirical formulas. See you there.